This is Mike coming back at you with another video on number theory. In the previous video, we saw some more sample problems where we take large numbers and we put them in canonical form, and then we use the canonical forms of two numbers to find their GCD. In this video, we're actually going to wrap up chapter 3. It's a very short chapter. We're going to talk more about prime numbers, and we're going to go through the proof of the theorem that there are infinitely many primes. But first of all, what I just want to show you is a very, very basic way that you could identify all the prime numbers less than some particular given number. In this case, we are going to come up with all of the primes that are less than or equal to 50, as that's the largest number that we have. And this is a very, very basic way, a way that the ancient Greeks would have determined what numbers were primes. It's actually called the Sieve of Eratosthenes. Sieve of Eratosthenes. It's a very hard Greek name to say. But I'll show you how this works in a person here. Here's a nice real-life sample here of how they would use this. So we have a chart of all positive whole numbers from 2 through 50 listed. We don't include 1 because we know that 1 is not a prime number. Any number that is strictly greater than 1 has to be a prime. So how this works is the first number that is listed and is not crossed out is known to be a prime. Once you know what that first number is, you then go on this chart and you cross out any multiples of that whole number. So the first whole number here that's listed is 2, so we know that's a prime, obviously. Now I'm going to cross out any multiple of 2. So 4, 6, 8, 10. Obviously, this is going to be all even numbers. So I'll just cross all these out right now. So we've crossed out all multiples of 2 that are on this chart here. We now move to the next number up that is not crossed out. We now know that that has to be a prime number as well. And we're then going to cross out any multiples of that guy that are larger than it. So the next largest number up that's not crossed out is 3. 3, as we know, is a prime. So now I'm going to cross out larger multiples of 3. And if it's already crossed out, then cross it out once more. That's all right. So 6, 9, 12, 15, 18, 21, 24, 27, 30, 33, 36, 39, and continuing, so on and so forth. Okay, move to the next number up that is not crossed out. That is a prime. We are going to cross out any multiples of that guy. So 10, so those are all the multiples of 5 that are obviously not primes. So we are going to cross those guys out. Move to the next number up. That is obviously 7. That's obviously a prime. Now cross out all multiples of 7. So 14, 21, 28, 35, 42, and 49. And then we would keep going with this. Next number up, 11, as we know, is a prime. So we'd cross out 22, 33, 44, multiples of 13, 26, 39 and 52 is outside of our scope. Multiples of 17 are 34, and next up is 51. Multiples of 19, 38, 23, and a 46, and then 29, 31, 37, 41, 43, and 47. So we've identified all of the primes now that are less than or equal to 50. Two, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, 37, 41, 43, and 47. So this is just a very basic way that you can figure out what are all the prime numbers less than some particular given number. This is kind of long, it's kind of tedious. You'd have to write out all these numbers and then cancel out the larger multiples and cross them out. So it is time consuming. It is a bit more tedious, but back in ancient Greece, this was a very clever way to figure out what are all of the primes. Just a quick term I would like to throw out at you if you haven't heard of it. We see that we have primes that are separated by, or we have primes whose difference is 2. 3 and 5, take the difference of 5 and 3, you get 2. 13 minus 11 is 2. 19 minus 17 is 2. 31 minus 29 is 2. 43 minus 41 is 2. Any two primes whose difference is 2, those are called twin primes. If you choose to look in the textbook on your own, you'll see a section or two where they talk about just twin primes, but just something I figured that I would throw out there, just in case you hadn't heard of it. So now this sieve is a way to locate all primes less than some particular whole number. But can we test to see if a particular number is prime or not? Is there a way that I can just determine if one number, say 67, is just 67 a prime number or not? Well, we can do that. We do have a test, and there's no real formal name given to the test, but I'll call it the square root test. And here's what the square root test is. If you have to determine if a particular integer n, which is positive and more than 1, is prime, you have to divide n by all primes that are less than the square root of n. If none of those primes nicely divide n, then n is prime. If even one of those primes does indeed divide n, then n is not prime. So one example here, the number 353 is a prime because no prime or no primes less than the square root of 353, which is just under 19, none of those primes nicely divides 353. Our primes less than 19 are 2, 3, 5, 7, 11, 13, and 17. And if you try to divide 353 by each of those primes on their own, you are not going to get a whole number. Another example, this is easier to think about off the top of your head, but the number 101 is also prime. The square root of 101 is slightly more than 10, but not quite 11. So I'm checking all primes less than 11. So that gives me 2, 3, 5, and 7. And if you try to divide 101 by any of those four numbers, you are not going to get a whole number. The number 837 is not prime because 3 is a factor of 837. The sum of the digits in 837 is 18, and 18 is divisible by 3. But we see that we have a much nicer way to see if a particular integer is going to be prime or not. You take the square root of that particular whole number. You test all primes less than the square root of that number that you were given. And if none of those primes does indeed divide n, then your given number is prime. So you may be asked on a homework or a quiz or a test to use the square root test to see if a particular given number is prime or not, and that's all you have to do. Now we come to the big theorem that I wanted to go through the proof of in this video. It's a very important result in the world of theory of numbers, and the proof itself is not too complicated to understand, and it's really kind of neat. So this is why I chose to include it in this video. So the theorem is that there are infinitely many primes. And we're going to need to keep a couple facts in mind as we go through this. And I give them numbers because we're going to reference the numbers as we go through the proof. We need the fundamental theorem of arithmetic, which we talked about a couple videos back. And then going back to the beginning of chapter 2, we said that if A divides B and A divides C, then A divides bx plus cy for any integers x and y. We're going to need to use these two facts in the proof of this theorem. So here we go. Here's the proof. The theorem, again, there are infinitely many primes. And we're going to prove this by contradiction. We're going to suppose that there are finitely many primes, and we're going to show that we lead to a contradiction in our reasoning and a contradiction in our logic. So if we suppose that there are finitely many primes, then we can number them. We can give every one of them their own name. P1, P2, P3, P4, P5, all the way up to and including Pn. And we can also write these numbers in ascending order. So P1 is the smallest, P2 is the next largest, P3 is the next largest, so on and so forth. This is where it's not very obvious how we would think of this, but what we are doing is a totally valid move, and it's going to help us get to what we want to come to when this is all said and done. We need to create some stuff. We need to basically come up with a possible case that would that shows that what we've assumed cannot be true. So how we're going to do that is we're going to define this number capital P. And what we're going to define capital P to be is the product of all those primes that we've stated. There are a finite number of them. I multiply all those primes, and then I add 1 onto it. Well, each of the primes by themselves are whole numbers, and they're greater than 1. So then, obviously, capital P is going to be a whole number that is greater than 1. By that, or since we know that, by the fundamental theorem of arithmetic, number 1, as we have here, we know that P is either a prime or it's a product of primes. Either way, there is some particular prime, which I call small p, no subscript, just some prime small p, such that small p divides capital P. We don't care what the prime is. It's not going to matter when we're all said and done with this proof, but we know that there is some prime little p that divides capital P. But we've listed all of the primes. We've given every prime its own name. So P then has to equal one of those P sub i's. P could be P10, it could be P1 million, it could be P47, whatever. But P has to be one of those P sub i's, and thus P divides this number Q. And I'm going to define this number Q to be just the product of all those primes. Just P1 times P2 times P3 times Pn. Because P is equal to one of those P sub i's. So we know that little p divides capital P, little p divides capital Q. Well, we said if A divides B and A divides C, then for any integers x and y whatsoever, A divides bx plus cy. So since this is true for any choice of x and any choice of y, as long as they are whole numbers, I can choose them to be whatever I want them to be. Let's nicely choose x and y to serve the purpose that we want them to. So I'm going to choose my x value to be 1 and my y value to be a minus 1. So I know little p divides capital P, little p divides Q. So therefore I know that P divides P times 1 plus Q times negative 1, or P divides capital P minus Q. But now if we make the substitution for what capital P and capital Q are, we're just going to get 1. Because P was the product of all of those primes, and then 1 added onto it. Q was just the product of all those primes. So therefore, we know that P has to divide 1. But this is our contradiction, because the only numbers that can divide 1 are either negative 1 or positive 1, and primes are not negative, and primes are greater than 1. So this is our contradiction. This is what tells us that what we have assumed cannot happen. It cannot be possible. So therefore, we conclude that there are an infinite number of primes. So this is a fairly understandable proof in the world of proofs of mathematical facts and mathematical theorems. There are some that are pulling a lot more tricks. This one, not too bad, pretty straightforward to follow with, and pretty straightforward to see what's going on. But this is just a nice little wrap-up of Chapter 3 and our work with prime numbers. Big thing from this video is using the square root test to determine whether or not a particular integer is prime. In the next video, we are going to begin Chapter 4 when we talk about congruences. My apologies. If you have any questions or comments, please be sure to drop them in the comment section below. Otherwise, until the next video, take it easy, guys.